let's go with first we complete the part of our AES as I told in last. Then we will complete about your lab part and then the question and answer, or if you have any questions, because I think tomorrow there is a holiday. Okay, so that what we are going to maybe meet after your exams. Okay, so that's also we are going to discuss when the thing is over. Is the PPT. Okay, so now in last one we have seen the DES, data encryption standard, but after some time, after a years of that is used, and with the 64-bit, the people are kind of with advanced machines, advanced configurations, infrastructure available with timing analysis and everything, they are trying to find the problems in that, so that the people came with the next one, that is the AES. Okay, so in AES I am not going in the detail of everything because it is somewhat kind of the way of explanation is similar in with the DES, the blocks is there. So here you can see it is a 128 bits. Okay, so it's like 16 bytes. So in DES, if you remember, we have a kind of 64 bit. So here they are increasing the plain text blocks, that is 128 bits. So with the increasing the box, what will happen, that for an attacker they require 2 raised to 128 kind of possible things, and then they can try it in that way. Okay, the key will be kind of a bytes in M, that is not fixed. Okay, so it is not like in terms of DES. And what will there, that according to the rounds the key is going to be expanded. So whatever the key that is used by user, that will going to be expand, right, so that it will be used for all the rounds. Okay, so it depends on whatever the number of rounds, that whatever the algorithm that you are going to use in AES, because in DES we have a 16 rounds fixed. Now in AES they are coming with a different version like 10, 12 or 14 rounds. So whatever the rounds, that whatever the encryption, that particular algorithm that you are using, the reverse way you have to use the decryptions, right? So if you are using a 10 round encryption algorithm, you have to use the 10 round decryption. That is the way you have to use it. So if depends on the number of rounds here. So if you are increasing the rounds, it means if you are increasing the rounds, it means I want more keys, right? Because for each round I require a kind of something somewhat a new key. So that's why my key length will be in terms of bytes is also increasing. So it will start with the 16 bytes with a kind of a regular 10 rounds. And if you want to go at more kind of rounds, now advantage of more rounds is that your complexity, sorry, your kind of complexity in a message is in garble is much more. So for a attacker it is hard. Now increasing the round, the other effect is that increasing the rounds will take more time, right? Even though it will be a fractions of whatever the seconds or minutes, whatever, but it will take somewhat a more time. So according to there is a need, that's you are going to select the rounds and you can go ahead. Okay, so this is what again in kind of they are going to put in terms of this kind of cubicle 16 bytes, and then you will use the different blocks, right? So and then after each blocks you will get a particular 16 bytes of output, and there are different rounds. Okay, so within each rounds there are kind of a transformations that what they are going to see. So we are going to see that what is the entire rounds. Now AES does not follow the fiscal structure. DES is follow the fiscal structure. It means they will divide in left part, right part, then do with the right part, left part here, and then try to swap here, so and so on. Okay, so that fiscal structure they are going to remove in the AES. They are going in a continuous structure, and every time you are getting your 16 bytes output and so on. Okay, so this is going in the last, only in the last round, whatever the last round is there. Okay, that they have a 3 transformations, and then they are going to take your particular final output. Okay, again it will go in a reverse way in terms of a decryptions, and this will be our key expansion. So now if you can see that some of this thing is similar, the way of explanation is similar in the DES. What is that? That is a key expansion, right? In DES also we are using the keys here and there. Now here the logic is different for a key expansion, but the meaning and the utilization of key expansion mechanism is required. Now there are rounds. So in each round they are doing something. Within each round there is a blocks is there, and what from that block they are going to work out. Okay, so same thing in a DES, we have a multiple rounds is there. Within each round, fine, there is their logic. Here there is their logic, but they require multiple rounds. And then for each round, they require a key, right? And you can see that as my plain text, that's our message I'm giving to each round is 16 bytes. The keys also I'm giving is of 16 bytes. Okay, so whatever my input key, that I have to divide in multiple keys, and each of the key is kind of, you can say, the 16 bytes. It will be go ahead. That is the way it will be there. Okay. So something is similar. So that is what you can say, that it is what a generalized process on encryptions, that there are multiple rounds. Each round you will try to do some garble with the messages, so and so on, so that in the reverse garble you will get the message in a decryptions. You will also expand the key, because you cannot ask the user that can you enter a 16 keys. Okay, if you will ask the user kindly enter 16 keys, it's like in an email, for example, if you are using email system, the email provider will ask you, well, one key is not, one password is not enough, you have to enter 16 passwords because we require 16 passwords. No, that's why the people are not going to remember it. So that's why with one password they are trying to garble the things and then they are going to use it. Okay, so this is what a kind of a structure is there. So it depends on whatever our kind of, you can say, the total 4x4 thing is there, and each of that is a 4 bytes, and depends on the number of rounds that they have compared to the last round. Okay, because in last round we have a 3 transformations compared to the last, all the previous rounds they are having a 4 transformations. And of course, as we know, in a DES we have a substitution, permutations. That's what we are going to use, the S box and P box. So now here what they are going to use, they are using this S box, substitution box. They are using some shifting the rows. That is what the word they are going to use, because here we have a 4x4 array, right? Here we don't have a left and right part. We have a straight 4x4 array of these 4 bytes, and then they are going to use some mixed columns, and with that they are going to use the end round key. So all these are, you can say, the some parts of the round, right? Within each round we require to do this thing. Okay. And then of course they require the XORs by anyhow. Okay, so that they will try to utilize. So that's why you can see in all our programs, in all our structures in security, XOR will be the kind of, you can say, the mostly gate that is used widely, because it is going to cancel the things. That is what the advantage is there. So this is what you can say the structure of AES. We are entering the plain text, then whatever the round key will be there, and then within each round, these are, you can say, the particular their structure, that each round will be divided in this total 4 transformations. So one transformation is substitution byte. This is the first one, first transformations, second transformation, third and fourth. Now you can see in the last round, if you are following a 10 round, they are only using the 3 one. Okay, so if whatever the number of rounds you are following in the last round, you have to take one less for that particular, mixed column. That is what the transformation they are not using. Other things they are going to use it. Okay, and in terms of decryptions, you can see they are going in a reverse order. Okay, so here it will be done last, these 3. This will be done here also in last, and then you are getting the message. Okay, now in terms of key, whatever the key that you are entering, that will be going to be expanded, so that all you are getting a different kind of a keys, because you know that if there are 10 rounds, we require 10 different keys. Each of the key is in terms of, you can say, total 16 bytes. So the initial key of a 16 byte will be transformed in a total 10 16 bytes keys. Okay, and then they are going to use it. So okay, so this will be my encryption process, and this will be my decryption process. Okay, so now the only thing is required is that what is the logic for this, all the 4 transformations: substitution byte, shift rows, mixed column, at the end round key. Okay, so this is a kind of the what we have discussed, that what they are using this end round key and so on, and same thing they have to use in reverse order. So let's go with the first one, that is the substitution bytes. Okay, so let me take an example. So this is my, you can say, 4x4 kind of a box is there, and it will give me the X and Y coordinate. Okay, and this is my substitution box. So from this one particular, this is a 4 byte, right? So from this they are getting this X and Y coordinate. Using X and Y, they will get a one particular block here, and that block will be replaced with that thing. Okay, so from each 4x4, I will take one part. From that, I will take the X and Y coordinate. Through that, from my substitution box, that is common between the encryption and decryptions, and okay, and that will be a generalized. Like we have a permutation or S box in DES. Here also there is a S box, but in DES we have 8 S boxes. Here there is a 1 S boxes that they are going to use in the round. Okay, and from that, using X and Y coordinate, they will get the new value. That's where they are going to use it. Now in a reverse order, through this S-11 again they are getting the X and Y coordinate, and through that they will get the block here, and through block they are getting this message here. Okay, so the same way they are going to here and there they are going to do it. Okay, so this is kind of one example in that whatever our message, this all the messages, for example this block they will get X and Y coordinate, and from that they will get the 87. That's why they are going to use it. So from each block you will get the next block, and that's where from again reverse from 87 again you are applying and you are getting the E. That's why they are going to do it. Okay, now in terms of a shift rows, as the name suggests, it is shifting something, right? But here again to make the things garble, okay, they will do something change. So it's like first row they are not going to shift, second row they will do only 1 byte shift, in third row 2 bytes, and in the fourth row 3 byte shifts. And again make sure this is not a regular shift, it is a circular shift. Now what is the meaning of circular shifts? That's you can see that first row they are not going to touch, right? So it is you can see this is my first row. Okay, so 4 bytes in each row, so total 16 bytes. So first row not going to touch, second row only 1 shift. Okay, and this is what a last our circular shift. Now in second row they are going to shift 2 times 2 bytes. Okay, so it means in our box 2 that jumbling they are going in a previous, and circular it means going in this way. In the last row they are 3 times. Okay, so that's why actually you can see the arrow is come in this way, so that's why they are going to use it. And similarly you can see first as it is, that's you can see here first row as it is, in second row shifting is there. Okay, then and then so and so. So that's why if you use the same logic here, you can see the first row as it is, they are not going to change, while in second row they are going to change. So that's you can see that this EC will be here EC, that's why they are going to use it. Similarly C3 that they are going to use it. So they are shifting the things, and this is a circular shift. Okay, just a one wild question. If they are not using circular shift, what will happen? Any guess? For example, if they are not using a circular shift, any guess what will happen? Just a wild question.
Next row first column element will be added to previous row.
Well, okay, one possible answer. Not sure with the columns. Any other answers? Means if I don't do the circular shift, what will happen?
Information
I will just do a shift. Fine. Either left, here they are using left shifts. I will do the left shift. Fine. I don't do the circular left shifts. What will happen?
Sir, maybe some information lost.
Well, yeah. Well, correct answer. If I don't do the circular shift, what will happen? Those the last one, they are going to be swept, or they are going to be removed, right? Or they will be going to be lost because it is overwritten. Okay. So that's why if you are losing some data here, it means your answer will be coming wrong. Your ciphertext will be coming wrong. And if your ciphertext is coming wrong, again in a decryptions, you won't get a recover of those data, right? So that's why the things will be mapped here in encryption decryption, that data is never required to be lost. So that's why always the circular shift will be always required here. Okay. Now the next one is the mixed column. So this is what our you can see the Galois kind of a field that they are using with generating functions, and whatever the some equations, polynomial equations. So now you can try to relate what we have done with the unit 1 some number theory. That's what we have used. So here we have our particular this 4 kind of 4 cross 4 matrix. We have another 4 cross 4 matrix, and using this transformation we are going to get the new matrix. That's where they are going to use it. So you can see that's how they are going to use it. So whatever kind of our this thing is there, then we will try to multiply with our kind of messages. This is after the shift rows, right? So and then we will get our particular answer here, and then it will going to be pushed here. So this is a transform from one to another array, but using some logic is there, so that equations will be playing a role. Whatever these equations that is selected, that is playing a role here. That is we call actually the mixed columns, right? So this is what a kind of arithmetic simple, that how they are going to use it. So it is actually what they are going to use it. This is they are going to convert in kind of a binary. So according to your degree of x, you will get some kind of a binary, and then you will try to do some modulo and try to use the XOR so and so on. So that's will actually give me this particular, our kind of something in mixed columns. Now the fourth transformation, okay, so first one substitution S box, second one that is in terms of that's what we have done is mixed columns, okay, third and this is the fourth one, sorry, second one is a shift rows, third one is a mixed columns, and this is a fourth one that is an add round key, okay, because key will also going to be play a picture here. So that's what they are going to use it, because you can see that till now we haven't used key anywhere. We have already know that for each round we require 16 bytes of key, but in the previous three transformation we haven't used the key. So now our task is whatever my particular this all the 4 cross 4 16 bytes that I will do the kind of XOR with our all this is 16 bytes round key, and then it will give me some answers. Okay, so this is actually the answer of our particular key. So now you can see that how the things will be there. Okay, so this is my starting state that they will kind of divide in particular starting sub bytes different, because I am going to 4 cross 4, and then this is my particular things, and now they are going to use the shifting the rows. Once they do the shifting row, this is my substitution S box. This is after this thing. Once after this is first transformations S box, second transformation shifting here and there. Okay, then the third one I will try to mix the columns using that equations, and then the final once I have the answers I will use the key of a 16 byte round key. Okay, for each round there is a different key, and then I will get the answer. Okay, so this is actually a round 1. Okay, so round 1 to whatever the round n minus 1, that's where there is going. In the final round they are not going to use the mixed columns, the other thing they are going to use it. That's where they are going to use it. Okay, so this is now the next one is the key expansion. Okay, so we know that for each round we require the 16 bytes of a key. So that's you can see that whatever my key is there, this is for each byte is there. Okay, in each row, so 4 bytes in a one row, total 16 bytes. Okay, and then this we denote in terms of W0 1 2 3, and we using some functions they are going to expand, do the XORs, and then they are going to use the W4, and then you can see that to calculate the next W5, the W4 with the XOR with something. Okay, so that's why you can see these logics they are going to garble the things more and more in a key, so that your key will be somewhat more and more kind of a unique. So it's we don't want that for a multiple round, because we have a total n round, right? So in multiple that rounds we have the similar key bits. We want to change the key as much as possible. We want to make it garble. Okay, and that is what the things that they are going to use it. Okay, and yes, this is a key example that you can try to see that this is initial our W0 1 2 3 using our their logic. Okay, so this is what the functions they are going to use our G functions. Okay, and then they will try to do the garble. So from this 4 they are getting this 4, again they are getting this. So for here this is, let's say this is round 1 2 3 4 5 6. Okay, so for each round they are going to use these things. Okay, and that's where they are going to get the keys, so and so on. So this will be actually total 0 to 43 means 44 keys. Okay, so because we have a 10 rounds, and each round there is a 16 bits is there, so total you can say the 44 keys that we total require. Okay, now this is an example of a round wise analysis, like what we have done in a DES. Each round we are going to see what is the output. So that's what they have done it, that after we start with the particular message in initial round, we are not using any other things, we are only adding this round key. Now from round 1, this is round 1 2 3 so and so on. Okay, and this will be the last, our answers will be there. They are going to use this particular all the 4 transformations, and then they will get the particular answer. So that now why we require this kind of analysis, because for an attacker viewpoint they want to see that how many things are repeating is there. Like you can see that here this AB8B. Okay, this is going to be repeat here again and again. They are going to do some change here. So even from an attacker viewpoint, there is a bit by bit analysis will be done, that what are the things that is common, what are the things that is there. So even if some output at an intermediate round will be taken by the attacker, they will try to get what is the key or what is the message. Okay, now avalanche effect. So I think now all of you know that what do you mean by avalanche effect. Okay, In a DES, what we have done avalanche effect is that the how many bits are changing. Similarly here also, that round by round, we will see there are two plain text having a single bit of change, and therefore each round, what is the number of bits is changing. So that's the kind of the same message. That's what they have taken in DES. So that they are seeing that how many bits are changing. So here tentatively you can see that this is 58 bits are changing. Okay, so it means that on a general way, in terms of this bits changing avalanche effect, in DES we are getting more changes, right? The number of bits are more deeper, while in AES that's somewhat less deeper. That's the bits is there. Okay, so that is what the avalanche effect is there. But ultimately, you can see that with kind of a 16 bytes, this is what the number of bits that they are going to refer in a 10 rounds. So if you are going with a more rounds, your number of bits refer are more, but the time is going to be increased. Okay, so you can do a more garble with a time is per minutes. Okay, so that's why it is there. Of course, the way we have done encryptions, we can go with the decryptions. Okay, so this is what in a reverse order, that's what we have to apply all the rounds. Okay, and then we will get it in a reverse order. That's why they are going to use it. So here they are going to use the whatever the mixed columns that what we have used. Here everything is inverse. Okay, so all the things are inverse that they are going to use it, because that is what encryption and decryption is there. Whatever you use in encryptions, the decryption is a reverse of that thing. Then and then you will get the particular layer out. Otherwise you cannot get it. Okay. Yeah, this is something that they have discussed about implement. So that even in 8-bit CPU, now I'm not sure why we are using 8-bit CPU now. Just a question. We have, Core i7 and those all our processors are there. Why we are using 8-bit CPU? It is a very too low processor. Any guess? Why even they are trying on 8-bit CPU? It is already, I can say it is we are Core i7, Core i5, so and so on with whatever the hard disk RAM that is obsolete. Now 8-bit is very less. It is very kind of, you can say in old time it was 8-bit, but just any wild question, why we yet it is 8-bit? They are trying to see. Is there any field where still 8-bit is, or this lower kind of a processor is still there in demand? I think ICT students can give answer. I think all of you, yeah, know the buzzword is IoT, right? So what is IoT in terms of, you can say the Internet of Things. So things are kind of very, you can say the low constraint device. They are having a low processor, low RAM, low memory, and so on. Then they are deployed in a hostile environment, and you have to take it. Okay. Now it's like, consider that if each of the sensor is of a size of our CPU in a desktop, right? For example, right now, if I'm using Core i7, this is my desktop. So you can see if each of the sensor is of that size, do you think that someone is going to use that thing that much widely? No, they are not maybe going to use it. So that's why sensor size is kind of a very small, tiny, so and so on. And to make that thing, the things within that particular sensors will be in a very cost effective, okay, and very kind of limited in a space and so on. So with that thing, they have a limited in terms of processors, in RAM and memory and everything. So that's why even in that data, when you get it from a sensors, if you have to apply, because it may happen that if attacker has probing on that area, the moment sensor is getting a data and it is transferring to another device, the attacker is in between maybe and then try to get it. So sometimes there is a way the research is also going on that even on those particular sensors, either Raspberry Pi, Arduino, or whatever the devices they are using for the sensors. So in those sensors, can you try to implement the AES? Because of course you don't want to compromise the security, because you are working on a sensor and the attacker is working on a high-end servers, right? So that's why you don't want to compromise the security. Otherwise, if you can use the, let's say you can say, fine sir, I can use the Caesar cipher. Okay, it is easy enough for a sensor to do it. Just do the one particular kind of addition and XOR. That's the only thing. Okay, but attacker does not have that kind of 8-bit CPU. Attacker is having a latest server, so attacker can try to get the answers from those. So there is no meaning to use those things. So that's why when the things are there, they're also trying to use that even for a low constraint devices. Can we try to use those kind of a ciphers? So that is what that they have done it on in 8-bit, on a 32-bit, so and so on, and then they are trying to get it that what is the answers, how they're going to work out. everything is there, right? So this is what they discuss about this thing. So let me now also discuss your practical, because tomorrow we don't have a lecture left, and make sure this practical you have to submit from next to next week. Okay, so don't assume that in next week you have to submit. In next to next week you have to submit, and I think according to my news or calculations, maybe you don't have a lecture because there is an exam in next week, right? I think you have every day 2 exam. Okay, is I'm correct, Badal and Jeet?
Yes, sir.
Yeah, okay, so I think there is no lecture. So, and again, you are busy in exam, so I don't want to give you whatever our 1 week thing. So that's why I'm giving you a 2 week time for this practical. That's I'm going to set. So you can start this practical from next weekend after your exam. So you will get a fair 1 week in that complete this thing. Okay, so this will be the Playfair ciphers of 6x6. We have done a Playfair cipher of 4x4 in our theory. Okay, so here there is a Playfair. So this is for example. Now you can use the crypt tool here. In online crypt tool, this is not there. So if you have installed the crypt tool in your machines, then you can use this thing. So this is my message. Okay, so plain text. This is my plain text. So what is the first step? It will divide in a chunk of two particular characters, right? So is a TE and ST. Okay, and here there is a no repetitions. If there is a repetitions, then there is going to use the X in between. So this setting is already there in your particular. You can see this is a key entry of a. So if there is a duplicate letters, it will be separated by X. Even it is a X, it is separated by Y. That's why they are trying to use it. And this is the key that's you have to use it. Okay. So once you give the key, so this will be 6x6 matrix. So now you can see that this is a Playfair. Okay. So you can see this is a Playfair will be there. Repetition is not, and the remaining letters of ABCD. Okay. So till Z they have used this thing. Now this is a 6x6. So it means from 0 to 9 also that's you have to use it. So this will be your you can say 6x6 matrix that's you have to prepare. So what is the input for your particular program? The particular key. Okay, so here it is a key that is there. So here key is a Playfair. From that you have to prepare this 6x6 matrix, right? So whatever the key element is there, that's you are going to put it. The remaining letters you are going to put it. So same thing is required on the receiver side. So same logic what you have done here in a sender side, same thing you can put in a decryptor side. So the key will be required. This key matrix is required in both the way. Now the things are very simple. It is encryption and decryption. So what we have done here, if you remember that our message is there. So this is what TEST. So this is TEST, and now TE will be 22U. They're going to take 22 byte. Okay, and here this is a TU. So that's why they are going to use it. So how you are going to use it? That's what we have done. Check out for the T and E here in these things. Okay, so this is my T and this is my E. Okay, let me try to remove the things so that you will be getting better. Okay, this is my T, this is my E. Okay, so there is a in a same row and a kind of a column where they are going to match. Again they are going to match here. Okay, so that's why they are going to match. So that V and C. Okay, so this thing you can see V and C will be there. Okay, so that's where in whatever the when you are going in a column and row wise, they are going to meet each other. That's why they are going to do it. Okay, if here they are luckily in a different kind of a rows and columns, so that's why there is no need. If they are in the same row, go in a circular wise, take it in the same column, go in a circular wise and take it. Okay, so that logic is same for a Playfair. It depends on whether you are using a 4x4 or 6x6 or 5x6, whatever the matrix that's going to use it. But the logic of Playfair is not going to be changed. Okay, so this is your encryption. You have to input the key and the message, and the output will be the ciphertext. Again, in a decryptions, you have to input the ciphertext and the key. You will get the particular message. Okay, so that is what the thing is there for in terms of your practical. Okay, so again, let me try to remind the deadline for this practical will be next to next week. Okay, so that you people won't get any confusions. I think I'm also going to put the deadline in your Teams. So that's why there is no doubt to you people. Okay. Okay, so even though, let me try to 1 minute.